Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the fourth video lecture on the subject of computer organization and assembly language programming. The title of today's session is HDL for combinational circuits part 3. Well, today we will start with a class quiz first and then a review of the script based simulation which we covered in the previous session. Then we will write HDL for some standard combinational circuits like decoder, encoder, multiplexer and demultiplexer. Finally, we will do the testing of these chips in the hardware simulator. So let's start playing. So the class quiz first. Fine. Dear students, you all know that a Fibonacci sequence is an infinite sequence in which the first two terms are 1 and 1, sometimes 0 and 1. But over here you will consider the first two terms are 1 and 1. And each succeeding term is the sum of the two immediately preceding terms. So this is the Fibonacci series 1, 1, 2, 3, 5, 8, 13 and so on. I want you to design a combinational circuit that receives a 4-bit binary number as input. The output generated by the circuit is 1 if the input number is a Fibonacci number. Otherwise the output is 0. I also want you to write down the HDL for this chip and verify the chip logic by loading it in the hardware simulator. While writing the HDL, you can assume that AND, NOT and OR chips are available to you. So I've also given you the chip interface, W, X, Y, Z. These are the four names of the input pins. Out is the only output. The chip implementation is missing right now. Okay, so let me give you a hint. Before you do that, I think you can make the two stable for these four input variables and one output. By writing out the two stable, later you can simply arrive onto a Boolean function. You can simplify the Boolean function using the Karnaugh map or the Boolean identities, Boolean laws. Once you have achieved the simplified Boolean function, simply draw the logic circuit using the AND or NOT gate chips already designed in the previous session. Write the HDL, verify the chip logic and enjoy. So I will recommend that you should stop the video right now and try doing that. I'm moving ahead. Well, this slide is a review of the script-based simulation of the XOR chip. The XOR.tst is the script file which is loaded in the hardware simulator. When the script executes, the simulator generates the output file XOR.out, and also compared to this XOR.out with the XOR.cmp file. And finally, if both the file matches, the simulator displays the message comparison ended successfully. If any one of you have not practically done it, I strongly recommend to do it first before proceeding any further in this course. Well, dear students, before I write the HDL code for the standard combinational chips, I will of course give you an overview of their behavior. But I will keep this thing in mind that you have already studied them in detail in your digital logic design course. So I will be a bit quick. Let us start with a decoder chip. Well, my dear students, a decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 power n unique output lines. If a binary decoder receives n inputs, it activates on one and only one of its 2 power n outputs based on that input, and with all other outputs deactivated. If the n-bit coded information at the input has unused combinations, the decoder may have less than 2 power n output lines. And the example of such a scenario is a BCD to 7 segment decoder, which is actually a 4x16 decoder in which the output lines from D10 to D15 are not used. A very simple gate level diagram of a 2x4 decoder is shown over here. This is a 2x4 decoder, 2-bit input and 4 outputs. Any one of these outputs will be 1 depending on what number is over here. So if the number is 0, 0, only D0 will be made high. If the input is binary 1, 0, 1, so D1 will be high. If the input is 1 0, that is 2, D2 will be high, and if the input is 1 1, that is 3, D3 will be high. These are the Boolean function for D0, D1, D2 and D3. So if you have understood this, let me move on to the implementation of this in HDL. So this is the implementation, very simple. The chip interfaces, we have two input pins, A and B, and the output we have D0, D1, D2 and D3. We have 4 outputs, and keeping in view this, D0 is equal to A complement and B complement. So you can see I have used 2 NOT gates to get the complement of A and complement of B, and over here this AND gate is generating the output D0, in which the first input is NOT of A and the second input is NOT of B. Similarly, if I talk about the last output, that is D3, which is equal to AB. So you see this AND is generating the output D3, which is the bitwise AND of the 2 inputs A and B. I think the code makes sense to you all. Okay, so let me move on to the next circuit, that is encoder. Over here I have shown you a 8x3 encoder. You all must be knowing that an encoder is a combinational circuit that converts binary information in the form of 2 power n input lines into n output lines. Normally used to encode various symbols and alphabetic characters to a coded format. An example is octal to binary encoder, which is shown above, that takes 8 input lines and generates 3 output lines. Similarly, you might have heard about the ASCII encoder as well, which have 128 input lines and 7 output lines. Fine, if you see the truth table of this 8x3 encoder, you can see these are the 8 input lines and these are the 3 output lines. If let's suppose D2 is 1, remember only one of the inputs is 1. If D2 is 1, we have output 0 1 0, that is a binary 2. If let's suppose D5 is 1, we have the output as 1 0 1, that is 5. There are 2 limitations of this simple encoder. The first is the output is 0 in 2 cases. The output is 0 when all the inputs are 0, and the output is 0 when this D0 is 1. The other limitation is if more than one input lines are high, the encoder generates an unpredictable output. We will see to this when we will jump onto the hardware simulator, and I will show you these limitations and I will tell you how we can overcome them. Fine, so this is the gate level diagram. Fine. Over here I have shown you the functions as well, using which you can generate these 3 outputs, A, B and C. A is equal to D4 plus D5 plus D6 plus D7. So we need to bitwise OR these 4 inputs to get the A. Since we do not have an OR gate with 4 inputs, we have an OR gate chip with 2 inputs only, so we have used 3 OR gates. The first OR gate is bitwise ORing D4 and D5 and generating an output W1. The second OR gate is bitwise ORing D6 and D7 and generating an output W. And finally, the third OR gate is bitwise ANDing these 2 intermediate outputs and generating the final output A. Similarly, the output B and output C are also computed. So I hope this implementation of the encoder is clear to you. And let me move ahead to the other combinational circuit, and that is the multiplexer. Well, dear students, multiplexing is a technique of putting multiple signals on a single data path. And a multiplexer, which is also called a data selector, is a combinational circuit that selects binary information from one of many 2 power n input lines and transmits it to a single output line. And the selection of the particular input line is controlled by a set of n selection lines. A 2-way multiplexer is shown over here. Suppose this is a 2x1 mux having 2 input lines and 1 output lines, A and B. And depending on this input line, that is this select line, this multiplexer will decide whether the input on this pin should be sent on the output pin or the input on this pin should be sent to the output pin. So the behavior is if the cell line is 0, this A will be placed on this out, and if this cell is 1, this B will be placed on this out. And the same behavior is shown in this truth table as well. You can see if the cell is 0 in the first 4 rows of this truth table, the output will always contain A. So this A is mapped over here, this A which is 1 is mapped over here. In these 4 rows of the truth table, the selection bit is 1. So the output B will be placed on out. So you see this B0 is placed over here, this 1 is placed over here, this 0 is placed over here, this 1 is placed over here. So an abbreviated truth table is, if the selection line is 0, the output is A. If the selection line is 1, the output is B. So this is the behavior of a 2x1 mux, and if we want to implement it, this is the Boolean equation, this is a circuit, and this is what the HDL code is. So it's very simple and self-explanatory. Let me move ahead. My dear students, if you have any questions, please drop your questions onto my YouTube channel, or you can always email me at arif@PUCIT. Okay, so now let's talk about the 1x2 demux. Demux, as you all know, is a data distributor. It is a combinational circuit that receives information on a single line and transmits this information on one of 2 power n possible output lines. The selection of a particular output line is controlled by a set of n selection lines. This is the opposite of the multiplexer. A 1x2 demultiplexer is shown over here. There is a single input line, and depending on this selection line, this input is either placed on A or on B. So if selection is 0, or whatever is there on A is placed on N. So if the selection is 0, this in is placed on A. So this in is placed on A. If the selection is 1, so this in is placed on B. This in is placed on B. I think this should be the other way around. Anyway, and this is the table that describes the same behavior. So if you know this, let me show you the HDL of this demultiplexer. This is the Boolean function for the 2 outputs A and B, and this is the implementation. We have used a NOT gate and 2 AND gates. Once again, hardware description language is a textual language, very self-explanatory. Okay, so now there is a question. Let's suppose there is a demux and there is a mux. We have a 1x2 demux over here with, of course, a single selection line, and we have a 2x1 mux over here with, of course, a single selection line. The 2 output of this demultiplexer are fed into the 2 inputs of this multiplexer. Suppose over here we have a 1, that is the in of this demux is 1, and let's suppose that the selection input is also 1. Now the question is, what is there on the out of this mux if the selection of this mux is set to 0? Can you answer this question? Okay, so if there is 1 over here, the input will be placed onto this B. So this 1 will move on to this place, and remember over here we have 0. And if there is a 0 over here, this 0 will be placed over here. So we have a 0 over here at the place of out. Another question is, what is there on the out of the mux if the cell is set to 1? And of course, now it's very simple. Over here we have 1, this 1 is placed onto B, so this 1 goes on to B, and since we have a 1 over here, so this B goes to out, so we have a 1 over here. So I think you have a clear idea now how the multiplexer and the demultiplexer are interrelated with each other. And this slide shows the practical application of multiplexing and demultiplexing in communication network. Well, a common use of these circuits is shown over here, that enables transmitting multiple channels on a single shared communication line. Suppose we have 2 two channels over here, the news channel and a movie channel, and we want to transmit both these channels via a single communication line. The selection bit of the mux over here is connected to an oscillator that produces a repetitive train of alternating zeros and ones. So transmitting one bit from each channel in each oscillation, and this is known as the time deviant multiplexing. So for one click, this one is placed over here, for next this 0 is placed over here, then this 1 is placed, then this 1 is placed, then this 0 is placed, and so on. And on the destination side, one can use the cell input of the demux to select the channel to watch. So this is a very common example of multiplexing and demultiplexing that is used in the communication network. An interested student can dive into the time deviant multiplexing as well as the concept of frequency deviant multiplexing. And I move ahead. Okay, dear students, now that we have understood, design and written the HDL for decoder, encoder, multiplexer and demultiplexer, it is time to make our hands dirty to verify these 4 chips in the hardware simulator. Let me move on to our hardware simulator. Well, our hardware simulator is already running. Let me load the decoder chip first. Let me load it. This is the 4th video. So we have the decoder chip. So this is a 2x4 decoder. You can see the 2 input pins A and B and the 4 output pins D0, D1, D2 and D3. Decoder written over here. In the HDL pane over here you can see the chip logic written in HDL, and if I click on any of the chip parts, let me click on this AND. Okay, so you can see in the part pin pane, this gets populated with the part pin, gate pin and current value of the selected chip part. Okay, now let's change the input of this decoder. Let me place 1 over here in the place of A. A is 1, B is 0, so that means we have a binary 2 over here, so D2 should be raised to 1. Let me evaluate. Yes, D2 has been raised to 1. Similarly, dear students, you can practice this. I think I just wanted to, for completeness, I just wanted to show you the verification of this decoder chip. Let me load the encoder now. Click this button, encoder.htl, load the chip. Well, so this is a 8x3 encoder. You can see the 8 input pins D0 to D7 and the 3 output pins A, B and C. Here you see the HDL code and the 6 internal pins W1 to W6. If I click again on any of the chip part, let me click on to this OR gate, the part pin get populated with the part pin, gate pin and the current value of the selected part. Okay, now let's change the input of this encoder. Let me set D3 to 1. Let me set D3 to 1 and click the val button. And you see the output is 0, 1, 1. That is 3 in binary. Remember, this is a simple encoder. So we need to ensure that only one of its input pins should be set at any one time. And if I set D4 as well as D3, now let me check the result by clicking this evaluated button. So now the output is quite unpredictable. It is 111, that is 7, which is not correct. So I have selected 3 and I have selected 4 and the output is 7. And solution to this problem is a high or low priority encoder. Moreover, if I set all inputs to 0, let me set all inputs to 0. So you see everything is 0 over here. And if I set D0 to 1, so you again see all outputs are 0. And solution to this problem is an encoder with enable input. And I'm leaving this as an assignment to you all to implement this logic in this chip. Okay, now let us now verify the multiplexer chip. Instead of loading the chip and doing interactive simulation, let me load the script file this time. The script file of the multiplexer, mux.txt. Okay. The script says load mux.htl, generate an output file, mux.out, and on completion of the script compared with the mux.cmp, and this is the format. And these are the 8 different set eval output commands which sets the value of the input pins A, B, and cell, and then evaluate and finally write the output in the mux.out file. Let me set the execution speed to a bit slow, and then click run instead of stepping into one after another. Okay, you see it is executing one command after another, and you see all these different inputs and different outputs coming in over here. And once we are done, you see the message comparison ended successfully. Let me come up over here, see the output file, which is this, and check the compare file, which is this, and you see both the files are exactly same. So that is great. Well, dear students, we are done with decoder, encoder, and the verification of the multiplexer chip. I am leaving the verification of the demultiplexer chip onto you. Please do that at your own time, and let me fall back to the slides. Okay, what is left? Okay, so that is it. So dear students, that is all for today's session, and these are the tasks you need to do. Perform the interactive as well as script-based testing of the chips that we have designed in today's lecture. Design different sizes of decoders, encoders, multiplexer and demultiplexer circuits. Write their HDL files and confirm the chip logic by loading them in the hardware simulator. Well, interested students optionally should also try to implement all the standard logic gates, NOT, AND, OR, NAND, NOR, XOR and XNOR with multiplexer. This is also a great application of the multiplexers. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.